My name is Tom Heron, and I head up market transformation at NFRC. As part of our Emerging Technology and Sustainability series, we have a very exciting presentation for you today. The title is Leveraging Industry University Collaborations to Drive Progress in Building Sustainability and Window Systems. One of our presenters is Dr. Nicholas Clements, who is a research scientist, instructor, lab manager, and manager for the National Science Foundation Industry University Cooperative Research Center in the Architectural Department at the University of Colorado. His research includes air quality, health, and well-being in the built environment and airborne infection control. Most recently, Dr. Clements served as the ASHRAE Environment Health Committee Chair and is currently a member of the ASHRAE Health and Wellness in the Built Environment Position Document Committee. Joining Dr. Clements, we have Madison Likins-White, who is a Ph.D. candidate at the University of Colorado Boulder, and her research focuses on the connection between window durability and thermal performance with the goal of understanding and incorporating the relationship between the two into energy simulation software to improve whole building life cycle estimations. Madison holds a bachelor's and master's degree in mechanical engineering, and she's been a licensed professional engineer since 2021. Two quick points. If you have questions along the way, please type them into the Q&A box rather than the chat box, and our presenters will address them when they can. And finally, we are recording the webinar, and we will post it on NFRC's website, so you can refer to it later or perhaps even tell your colleagues and customers about it. So with all these credentials at hand, I'm confident we all have a lot to learn. So I will hand it over to Dr. Clements to get us started.
All righty. Thank you, Tom. Pleasure to be here. Thank you for having us. And yeah, so I'll kind of kick off the talk today, talking about this, in short, IUCRC, called the Best Center, and then Madison will take it away from me and talk about some of the research she's done through the Best Center. So yeah, so those are the two parts, and we'll try to stop halfway through when I'm complete, answer any questions while we transition to Madison's talk. So let's get into it. So yeah, the Building Energy Smart Technologies Center, or the Best Center, is an NSF Industry University Cooperative Research Center, or IUCRC. These have been around a while. There's a few kind of in this field. Center for the Built Environment at Berkeley is a former IUCRC, and now they've kind of grown to the point where they can be self-sustaining. But the three kind of major aspects of an IUCRC: first is to kind of develop partnerships with industry collaborators, universities, and government agencies. So for example, with this research, we have NREL acting as mentors with Madison's team. But we also have a large kind of a growing consortium of other industry partners that I'll get into later. The NSF funds primarily kind of operation management costs, whereas the Industry Advisory Board, or industry collaborators, their annual fees directly fund research and education training activities. So pretty low overhead with that is kind of an advantage. And the Best Center is a collaboration between CU Boulder and City College of New York. So we have colleagues kind of spanning the Colorado and New York City, each with their own specialties and research interests. The mission of the Best Center is pretty broad, kind of focused on advanced energy systems for building cities and grids, and looking for them to be intelligent, resilient, and efficient. The main research themes for the Best Center are smart buildings, smart building materials and systems. So for example, our window research portfolio typically falls into this theme. Integrated energy generation storage systems, building retrofit applications, smart building energy systems, and smart grid systems. And then as we kind of think about those themes, they can be applied kind of across the building typology. So whether it's a building or a community or a city, We have research that's looking at energy efficiency, controls, resiliency, thinking about affordability, comfort, and productivity. And all those kind of aspects of the built environment can be looked at from the demand side. So kind of thinking, individual buildings, building technologies. On the management side, so how do you get kind of buildings to integrate with grids or other energy distribution systems? And then how do we get buildings or communities even interacting with power generation broadly? The BEST Center, this is kind of the breakdown of a lot of the components of it. We are in our second year currently, our second funding year. So the original proposal was granted in 2021. Our phase one will go through 2026. Then we'll be applying to a phase two. So these centers are intended to kind of last for a few years to build sustainability as far as industry collaboration and fees go, and then kind of be set free. As I mentioned, we have two university sites, U Boulder and CCNY. We have one former kind of leadership member that moved to the University of Albany, so we're also able to tap into their capabilities. We have a website. A lot of this information is available there, as well as some overview slides that go into a bit more detail on this. We currently have 5 full members, 2 associate members, and 7 affiliates in our industry advisory board. And I'll kind of go into details of what that means and what that entails here in a few slides. We kind of run on an annual basis. So projects are usually begin funded in the fall. That's when kind of projects that have agreed upon in the prior funding year kick off. And then we start the process of thinking about the next funding cycle. So kind of in the winter, the faculty, or sorry, in the fall, our industry advisory board and our faculty meet to talk about themes or research topics for the next year. And then in the winter, January, February time, the faculty will kind of respond to those research ideas, writing proposals. We have a spring industry advisory board meeting where those proposals are voted on for funding. And then the summer, we work on getting the money to the PIs. And by the next fall, we kick off those projects. We typically have 2 industry advisory board meetings, one kind of in April, one coming up at the end of November. And at this upcoming one, it'll be in New York City. We will be kind of establishing the list of research topics that faculty will respond to for proposals next year. So that's kind of the cadence of what we do at the center. Organizationally, we have representation from both CU and CCNY as far as directors go. I manage this, so I'm kind of the link between a lot of the components. We have NSF is pretty heavily involved as far as evaluating, make sure we're on track as far as the number of members we have. And our industry advisory board is involved heavily in kind of how do we operate the center? What do they need to know about, or how do we get their ideas? So it's pretty interactive with our industry partners. As far as kind of the faculty and the research capabilities within the center, these are the 6 kind of CU Boulder faculty currently engaged. The site director or the executive director of the research center is Monsef Krardi, and he's kind of pretty heavily involved in a lot of retrofit technologies, thinking about electrical integration or HVAC integration with retrofits, as well as kind of large-scale energy efficiency programs. John Zai kind of is in similar research field to my own, thinking about air quality, but also heavily involved in the research on fenestration and windows. So he is the kind of PI on the project Madison will be talking about. Kyrie Baker, very much kind of an electrical engineering focused researcher. Gregor Henze focuses on the controls side primarily. Could be anything from HVAC controls to grid integration. to how those controls impact humans in the building. Will Shrubar focuses on some cool research on biomimetic materials. So if you want your concrete to repair itself, Will's the person to go to. And then Michael McGeehee has some interesting research on solar panels as well as window tinting technologies. And he's part of a startup called Tint that has been involved in the center. A few of the Seaboulder research capabilities. I'm the manager of the Larson Lab here on the first one. This is a fairly large facility. I'm literally sitting above right now, where we have 2 chambers, each with their own HVAC system, and we can do fairly extensive HVAC and thermal system related research, air quality research. We also have the lighting lab, the living materials lab, building electrical system modeling capabilities, Michael McGeehee's lab focusing on solar cells and dynamic windows. And then we have this institute called RACI, or Renewable and Sustainable Energy Institute. And this is a collaboration with NREL. So we have some pretty tight connections with them through that institute. On the CCNY side, Ahmed Mohammed is really focused on kind of the energy systems and critical infrastructure research. So how do you keep your electrical grids running in the face of natural disasters, for example. Jorge and Pratap both kind of work on energy systems as well as the kind of the atmospheric research side on a city scale. And as does Mark. Mark Aaron also works on that. And then we do have good connections with the CUNY Building Performance Lab with Honey Burke, Michael Bobker, and Duncan Prawl. And they've done some great research looking at how do you manage kind of energy systems within a large city like New York City. So these are a few of the research capabilities on the CCNY side. I mentioned Building Performance Lab, BPL. They do quite a lot of work with New York City Department of Administrative Services, and quite a bit of capabilities there as far as kind of analyzing a city level energy efficiency program. Ahmed's Smart Grid Interdependencies Lab really focused on kind of smart distribution of electricity and thinking about these resiliency topics. We have the Coastal Urban Environmental Research Group with Jorge, and they've done quite a bit of work kind of looking at satellite data and how to use remote sensing capabilities to manage a grid. And then a place that we'll be visiting for the upcoming Industry Advisory Board is the Advanced Science Research Center. And they have quite a bit of capabilities as far as research tools and facilities to conduct kind of benchtop research. So our Industry Advisory Board, the role of the IAB in the center is kind of listed here. They're heavily involved in strategic planning. So kind of who do we need to reach out to? Who do we need to bring into the Industry Advisory Board as far as companies and organizations? They vote biannually on what's going to be funded and what is going to be kind of in the proposals. They also act as mentors on projects. So we try to make sure that at least one Industry Advisory Board member is attached to each project. And that's primarily to help kind of define scope initially, define deliverables, and mentor the students, the graduate students that are working on these projects. And it does offer the opportunity to build that collaboration and potentially hire the researchers at the end of their tenure. Yeah, and we have a chair and vice chair. Sasheen from Ream came in as our chair in the last year, and Sylvia came in as our vice chair. And Sylvia will be giving a keynote at our upcoming Industry Advisory Board meeting, talking about the efforts in New York City towards decarbonization. She's from Con Edison. These are our current members. So we do have a couple members from the fenestration world with Cardinal and Alpin, and both of them are involved with our Windows research. But we do have quite a few other groups, and in a few slides I'll kind of talk about the categories that all these groups fall into currently. Really quick, as far as getting involved, it is an annual membership program. So full and associate members are the members that vote, whereas affiliates, it's a little cheaper. There's no access to IP licensing as an affiliate, but you do kind of still have a lot of the benefits as far as accessing the research portfolio and kind of networking and hiring the students from CU and CCNY. The major note here is that we kind of look at this as an opportunity to externalize R&D, and through the NSF program, we can limit the overhead to less than 10%, whereas most universities will charge closer to 50+% for industry research programs. So this is a kind of an opportunity to externalize that, build research connections, and eventually hire potential graduate students. A few of the other benefits, one opportunity is the NSF intern program, where NSF will pay for a graduate student to work at an industry advisory board company. And so the company doesn't have to pay any money for their salary. So that's one that we're looking to use more in the future. And then, yeah, the full and associate members do have the ability to license IP generated through the center, and use these state-of-the-art facilities we have to conduct research. And I'm sure Madison will go into detail of some of those research capabilities. And then, yeah, you know, there's quite a bit of networking at the industry advisory board meetings. We develop and send out a bi-monthly newsletter covering kind of, you know, ongoings at the Best Center, but also ongoings in the building industry as a whole. And then we do have opportunities to develop webinars for our universities, where companies can kind of present the latest and greatest in their research or capabilities portfolio, and again, kind of work on hiring. So our industry advisory board currently falls into these 6 categories. So we have 2 utilities companies, 1 kind of HVAC thermal systems company. As I mentioned, two companies that fall into fenestration, a couple of municipalities, a fairly large contingent of consulting groups, and a couple groups, companies related to controls and sensors. We're always looking for new members, and we're planning to kind of grow our portfolio as the center, you know, increases in age. So these are kind of our target verticals over time. As you can see, it's pretty comprehensive as far as the building systems go. But currently we're kind of getting off the ground. These are kind of a breakdown of our faculty and how they connect with each vertical. So this is mainly to kind of show that we do have pretty good representation as far as the 2 universities go across these research verticals, and pretty wide breadth as far as what we can research with the center. And I'll wrap up by kind of introducing a few of the projects that were funded last year, and then introduce a few of the projects this year. So Madison will be presenting this first project, Evaluation of Field Methods for Assessment of Architectural Window Degradation. As I mentioned, this is a collaboration with NREL, with Rob Tennant there, and John Zai here at CU as the PI. We also have projects, quite a few projects centered around heat pumps. So this next one is kind of a research project for modeling heat pumps. The number 3 here is a building performance lab project last year, focused on modeling and trying to understand kind of how do you analyze a large portfolio of buildings. So our municipalities and utilities are very interested in this type of capability. And then the other 3 projects that were funded last year, the first is kind of this remote sensing type capability using satellite data to understand energy use in a city. Number 5 here is a building retrofit project, thinking about how do you use insulated panels that you can attach to the outside wall of a building, to add some to add insulation when needed. And then the last one is a controls project using reinforcement learning to kind of inform controls. And a couple of these projects have continued to be funded. So the Madison's project, Evaluation of Field Methods for Assessment of Architectural Window Degradation, was awarded a second year of funding. So this project will continue for another year. The other project that's funded this year that I'll bring your attention to is the evaluation of hygrothermal and energy efficiency and condensation risk of secondary windows. So this is a project that's just kicking off that may be of interest to this group. And a couple others kind of here, I'll point out, we do have a couple of heat pump projects. And then Gregor's project from last year on reinforcement learning is going to go for a second year, but it's going to think about how do you include human feedback in these control systems. So that's it from me. I'll be happy to answer any questions. I don't see any in the Q&A, but feel free to put those in there. And I will transition over to Madison.
I'm ready whenever you are, Nick, if you think I should get going.
Cool, yeah, go for it.
Okay, great. Yeah, so my name is Madison, and I'm in my third year of my PhD, and just going to talk a little bit about this project that was mentioned by Nick that I'm working with under this BEST Center. So essentially, it's a Windows degradation project, and kind of our key objectives that we started out with at the beginning of the project was to determine the effectiveness of different window thermal field measurement techniques. So doing a lot of research into what exists and what we could potentially add that hasn't maybe been done as much, looking into measuring U factor, the solar heat gain coefficient, and some other parameters related to window degradation itself. So we really want to understand those deterioration mechanisms and basically create a link between window durability and window thermal performance. So we know a lot about how windows operate on day one and what their rated U factor is, but we don't really know what happens to that U factor and other thermal elements of windows in insulated glass units as they get older and exist in buildings, through their 40, 50 years life cycle. So we really want to create a link between the durability and that thermal performance. And then the ultimate goal is to kind of put that relationship into simulation software so that we can get a better idea of, again, the overall life cycle impact that this deterioration could have on building performance. Because most of our building simulations, again, you just put in U factor day one, whatever it's rated, and then it'll spit out your energy consumption. But how is that actually going to change over the entire life of this building based off of how the windows themselves are also changing? So those are kind of the key objectives, and I'll wrap back into those. I kind of want to highlight that this research is really broken into two parts, at least in my mind. And part one is this field validation of some measurement techniques that we want to look into. And then the second portion is kind of the simulation half and merging those two together. So that was not working. There we go. So basically the first step that we did was this heat flux meter method kind of recreation that we did in the lab at NREL. So we used the differential thermal cycling unit that basically acted as our outdoor air condition. We were able to control it to any temperature we want, and also any sort of relative humidity as well. So we got these IGU samples and kind of decided to look at our two extremes. So the table over here kind of shows that we had 4 different samples that represent basically a brand new window. So it had a low E coating, argon fill, and then the other glass was just clear. And then we wanted to take a look at that same window, but with no air fill, and then also that same window with no low E coating. So essentially the low E argon fill represents a brand new installed window, whereas this clear air fill is going to represent like a degraded window in that sense. Again, definitely representing extremes, but the goal of this heat flux meter method in the lab was to see if it was sensitive enough to basically help us, or sensitive enough to see if we could detect changes in U factor due to the changes in low E coating or gas fill. Because if we put in these extreme examples in this lab setting where everything's perfect and still can't get these measurements sensitive enough, then there's no point in really going out in the field and attempting it as well. So what we did is we put each of those 4 different samples into this unit, and we were able to control our temperature differential across the 2 sides of the unit. So we did 10 degrees Celsius, 20, and 30 were our 3 different temperature differentials we measured at. We ran each of these for about 10 hours over 3 different times. So we have a ton of data. We chose 10 hours just so we could get close to steady state. So kind of our governing equation here is our heat flux equals the U factor area times that change in temperature. These heat flux meters here are going to measure our heat flux. We know the area, we know the temperature differential. So then we're basically calculating for this measured U factor and then comparing that to what the manufactured rating U factor was. Oh, sorry, I had an alarm set. So again, this was just to determine how close was our measured U factor or our calculated U factor to the manufacturer. And was this close enough, was our percent error low enough to say when our gas fill is low, we could tell there was a change in U factor. When our low E coating is low or deteriorating, we could detect that change in U factor as well. So I have some graphs here, and again, lots of data that we can kind of dig into if we have the time to, or if questions come up, but I really kind of want to go over what the key conclusions were from this. And essentially we found that the percent error for at least these 2 samples we have up here, so our low E argon coating and low E air, we found a percent error from our measured U factor to the known U factor ranging from about -2% to -10%. Okay, so we found that actually this lower temperature differential gave us higher accuracy, or this lower percent error, which wasn't really expected. I was thinking the opposite. If we had a better or a bigger temperature differential, then we'd have more accuracy, but we actually found the opposite. So this basically kind of gave us some insight to see how the different temperature differentials affected our results, and found that these extreme conditions that I believe is the ISO 9869 says to, you really want to have a bigger temperature differential. We found that maybe that's not as necessary as we thought. Moving on to our other samples as well, we found this percent error still around this 2% to about -8.6%. And essentially what this percent error told us was that for any changes in gas fill, the percent error was higher than our percent difference in U factor. So we know how much the U factor should have changed going from full argon fill to no argon fill. And that percent difference was maybe 4 or 5, but our error was higher than that. So if we went out into the field and tested and got a U factor that was lower or higher than we were expecting, we wouldn't be able to really confidently say, oh, that's due to a loss of gas fill. It could just be the error that we have in this measurement technique. We did find, however, that with low E coating, that percent difference of having a brand new low E coating between the no low E coating. So percent difference between those U factors was around 50%. So in that case, this method seems sensitive enough to tell us that if we had this really huge difference in U factor, we might be able to say, okay, that is telling us that there could be some low E degradation in this unit that we are looking at. So basically overall, and I kind of come back to conclusions again, we found that this method alone really isn't comprehensive enough to tell us everything we want about the thermal performance or the degradation of an IG unit in the field. I have to catch my breath a little bit. So the second half of this project that we've worked on so far was this simulation that we did. So we just took a DOE reference building that was a medium-sized office. It's a bit of an older model we used. I looked, is about 2004. So we definitely want to kind of repeat this with a newer building to just get kind of a building that's more representative of what's in the stock today. But the main goal of this simulation was to really determine the most impactful performance metrics for degraded IGUs. So again, really kind of taking a look at how much does loss of gas fill in an IGU affect the overall building performance, and then how much would a low E coating, how much effect does that have on the overall performance? So the goal of this was really to just give us more information about what we should focus on actually measuring when we get into the field. So we kind of essentially set up this simulation the same way we had our samples in the heat flux meter method. So we looked at all of the windows being brand new, have low E coating, argon fill, and then 4 different samples all the way down to, well, what does our energy consumption look like if we just have clear windows, no gas fill? And what we really found was that if we look kind of at these first 2 and last 2 groups together, that is showing us the change in our total zone cooling just for a loss of gas fill. And there's really not a huge difference. Heating, we have a little bit more here. We can see from about 5% and 2%, but it really indicated to us that loss of gas fill wasn't having a huge impact on the overall building consumption at the end of the day, whereas the low E coating was much more impactful on the overall zone loads. So this basically just told us that low E coating is kind of what we wanted to really zero in on. If we have to just pick a few parameters to really focus on, we really want to look at that low E coating just because it had a greater impact on the overall building consumption in this simulation, and that was kind of expected as well. In general, we kind of knew that the low E coating was going to have a bigger impact just based off of how much that changes the U factor as well whenever you have a low E coating versus not having one. What I thought was interesting about this simulation, though, that I really wasn't expecting at all, was that the changes in U factor just overall had a greater impact in our heating condition compared to a cooling condition. So this is really going to become more important when we talk about, you know, what needs to be changed in different climate zones. So if you're really heating dominated climate zone, you're going to care more about gas fill than maybe if you're in a cooling dominated climate zone. So kind of wrapping up those conclusions again, we, from this heat flux meter method, found that the gas fill changes really can't be detected using this heat flux meter method on its own, but the low E coating changes maybe could. So this tells us we need some additional measurement techniques. Looking maybe at the spark-like is something that NREL has, and they have some other new techniques we're kind of thinking about adding in to hopefully combine those 2 together. So the heat flux meter method can tell us a bit about the low E coating, but maybe we can have this spark-like tell us more about this gas fill. Our simulation conclusions just really confirmed to us that the effects of the low E coating are greater than the effects of the gas fill, and that this loss of low E coating in just our glazing can trickle down to all other building components and leading to higher operating costs, and that these energy changes occur actually in all climate zones. So the simulation, I just showed the results from a single climate zone, but I actually did it for all climate zones and saw essentially the same trends in each climate zone, just to varying degrees. So leading into some of our future work and plans that we have for this research, since we know the low E coding is going to be of great importance, we want to do kind of a small scale test on the optical properties of different low E coatings. So measuring the transmittance, reflectance, and emissivity with a spectrophotometer. So we want to look at some hard coat, soft coat, and even just like a kind of baseline clear sample, and compare those optical properties, and then essentially throw them into a chamber that is super hot and super moist, kind of degrade the low E coatings on purpose, and then put it back into this spectrophotometer and get all these readings again. So we really want to see which optical properties are going to be most affected by that degradation, to again just inform us about what we should focus on in field, because right now we can go into in field and measure everything, but then we don't really know what's going to be most useful for us. So we want to kind of start on a smaller scale and really try to hone in on just a few measurement techniques to make this a bit more reasonable and achieve the overall goals. So that's kind of what's up and coming right now at NREL, is getting those tests going. We also have a new master student that is going to be helping out with identifying some buildings on NREL and CU campuses that would be good for, or good candidates for, this in-field measurements. So we really want to get a range of buildings of different ages, because we're looking at window degradation. So we really want to know what the age impact has on thermal performance. What about orientation, different types of coating, different types of gas fill, etc. So he's going to start looking into what buildings we can have access to and get us just a good starting point to get into the field and start taking some measurements. So once we have those kind of identified, we would incorporate this heat flux meter method. This is an example of a spark-like. We might have some new optical measurements, this EDTM power meter. We kind of have all these other little pieces of equipment that we are trying to think of, like, how can we use these to our benefit and get the information we want, and start moving on so that we can start this data analysis process to develop a correlation between degradation. So again, like that age, orientation, etc. of the window, how that links to its actual thermal performance. So once we kind of have this, in my mind, hopefully it won't be simple, but, maybe an equation or some sort of correlation that we can put into Energy Plus and Open Studio, so that we can analyze those overall lifetime energy impacts for a single building. And then past that, even, we want to do that for the entire building stock. So again, at NREL, they have something called Comstock, which is basically in building energy modeling, but for all of the commercial buildings in the US. So you want to see, how is the energy impact going to change from saying our U factor is constant to now saying, oh, actually our U factor is changing. What is that energy impact on a single building? And what is that energy impact if we apply it across all of the commercial buildings that are in the United States? So that kind of is leading into these outcomes. Again, this database for the buildings that we want to do this testing on, developing this in-field measurement technique that can be repeatable, because we want people to be able to use that and potentially improve retrofit analysis as well. Create this relationship or link, or this model that is going to link window age in our energy performance to improve our energy consumption prediction and estimation of utility needs when we start looking at the overall building stock of the entire country. And I believe that's my last slide. So I'll go ahead and stop sharing my screen for now. And yeah, I can take it back to you, Nick, if you want.
Yeah, thank you, Madison. Yeah, and thank you all for being here today. If you want to ask a question, feel free to unmute or pop your question into the Q&A box. But we do have a few minutes left if there are any questions. And Tom, if you have any additional comments, feel free to.
Oh, thank you both. I just wanted to thank you for being here today. And this is really fantastic information. And as you were talking, it reminded me of the conversation we had before we started about how today's challenges and opportunities in green building and sustainability are so dynamic that the talent to address them doesn't reside with any one organization. And that's why it's so incredibly important for us to collaborate, leverage one another's talents and skills. And I'm sure that you guys set the foundation for more of that here today. And thank you very much for that.
Yeah, thank you for the opportunity.
So if we do have any questions, this is a rare and unique opportunity to tap in to our presenters' expertise.
Oh yeah, I was just typing out actually a question about this IGU width. I believe that it was around an inch for the IGU sample, so about 1/8 of an inch for each pane of glass, and then I want to say 5/8 for that air gap. So we really went with just kind of what was a standard or commonly used IGU for commercial buildings. And then I'm going to read your second half of the question and get back to you on that.
Okay, are there any other questions, Madison or Nick?
I want to address the second half. So change in emissivity likely associated with the change in the solar heating coefficient that'll impact energy use. That's something we haven't looked at yet. Solar heating coefficient is something that I've done a little bit of reading on how to measure in field, and it's extremely difficult. And so not a lot of people have a good way to measure that. And so that's definitely part of this research, is hopefully to find some way that's a bit more accessible. For emissivity, that is something we really want to look at on kind of that smaller scale that I was talking about with the our low E samples we have, is looking at the emissivity of those and how that can come into play of an overall unit in measuring in field. So yeah, something we definitely want to look at, but just haven't gotten around to at this point.
All right, any others before we wrap things up? Okay, if not, that concludes our webinar for today, and we will let you know about future installments. We have some very exciting things coming along, and including something already scheduled for December, and we'll be providing more information about that. So we hope to see everyone again soon. Thank you for being here today.
Thanks, y'all. Take care.
Thank you.